Given a unit circle, we pick 2 points at random, measure the distance between the 2 points and record them somewhere. Then choose another pair of points randomly, measure the distance between them, and record this as well. Pick a lot of other pairs of points and measure the distances, and then we consider the average of these distances. The question in the title basically means the average when we take larger and larger number of pairs. It turns out the average distance would be 128 over 45 pi. So there you go, here's the answer. Don't forget to like, subscribe, hit the bell, and comment below. Okay, I'm joking. The video hasn't ended yet. Where does this 128 over 45 pi come from? To explain this, we will need a video series, but along the way, we will learn more about probability and calculus in general. This video will deal with the first 2 concepts because they can make the problem more mathematically precise, while the remaining 2 explained in the next few videos make the problem much more manageable. However, before actually solving the problem, another video is dedicated to estimating the answer numerically, because this is not as easy as it looks. To really understand the problem, we have to know what random means more precisely, because we are picking pairs of points randomly for calculating distances. Ideally, what we want is that our points are roughly uniformly distributed. This means that if there are 4 points in this box, if I move the box elsewhere, it should contain more or less 4 points as well. The areas of the boxes can vary, but the number of points in these boxes should be more or less the same. In other words, the density of the points should be the same across the disk. However, the density of points depends on the number of samples taken, so a better description would be having the same probability across the disk. This means that the probability of any point being in this box will be the same as that in any other box as long as they have the same area. The box does not have to be rectangular and any shape would be fine, but rectangles are just easier to demonstrate. Anyway, the probability of a point inside a region would be proportional to the area. In other words, the ratio between probability and area of the region is a constant. This quantity on the left is probability density, so actually we were not thinking about probability at any given point when we say same probability across the disk. We actually meant probability density. We can actually calculate this constant of probability density. When the area concerned is the entire circle, i.e. the area being pi, the probability is of course 1. However, in other cases, this quantity can depend on position, i.e. a function of the position vector x. This function is, unsurprisingly, called probability density function, PDF for short. The way to calculate the probability density at one single point works like this. Pick any region around the point and calculate the ratio between probability and area of the region. If we shrink it, this ratio might change a little bit. The PDF at this point is taken to be the limit of this ratio when the region shrinks to nothing. In this case, the position vector is in 2 dimensions, and so the denominator is naturally the area of the region. If we are working in 3 dimensions, the denominator would be the volume instead, and so on. It might seem like the discussion of PDFs is irrelevant, but if we have different probability density functions, then we will have a very different distribution of points and thus different answers to a problem of average distance. In general, whenever you say random, you should always specify the PDF to avoid getting different answers to the same question. This is basically the crux of the infamous Bertrand's paradox, which might be a story for another time. Anyway, the next thing we need to deal with is the word average, because there is a continuum of possible distances and pairs of points, but let's deal with the simpler situation first. What will be the average of a function like this? Intuitively, we should sample some values of the function, so let's denote the y-coordinates as y1 to y5, then our estimate of the average would be summing them up then divide by 5. On the other hand, we can consider the area of these rectangular strips. We chose the points at regular intervals, so the area of the strips is the common width times the sum of the y's. With that, we can replace the sum by area over the common width. However, 5 times width is precisely the length of the interval on which the function is defined. So if the function is defined on the interval AB, then the 5 times width here can be replaced by B minus A. If we sample more points, then the area of the rectangular strips becomes closer and closer to the area under the curve, so the average can be found with an integral. Now notice that the denominator is the length of the interval, and we are integrating over the interval. If the function takes in higher dimensional input, then the length of the interval would be generalized to the volume of the domain. And instead of integrating over an interval, we integrate the function over the domain. In fact, the prefactor is the probability density across the domain, so if the PDF is not constant, this average will be more complicated. Anyway, to determine the average distance, we need to first determine the domain of the function. Here, the function would be the distance between the points x and y. X is a point in a unit disk centered at the origin, and of course, Y is also a point in the unit disk. That means the domain is the ordered pairs of points in a unit disk. Even though this is a 4-dimensional domain, it is useful to think of it as a sort of square, where each side represents a unit disk. So calculating the 4-dimensional volume of the domain U is sort of like calculating the area of a square. It would be side length squared, but here we generalize the side length to be the 2-dimensional volume, or the area of the unit disk. Area of a unit disk is pi, so the volume of the domain is pi squared. So going back to the formula for the average of a function, we can simply substitute the domain and the volume here. To make this integral more explicit, we can choose to represent the points in Cartesian or polar coordinates. However, whichever coordinate system you choose, the resulting quadruple integral is really horrible. If we don't know the answer, there is no reason why this evaluates to a nice closed form answer, which is why in the next video we want to numerically estimate the answer first. Then the following videos will explain the remaining 2 concepts that allow us to solve this problem analytically, which will be in next year, because this will be the last video in 2020 from me, so I would like to give a big thanks to all of you. In the beginning of this year, I only had 200 subscribers, and as of recording, I have more than 2,000 subscribers. Merry Christmas, or if you don't celebrate Christmas, Happy Holidays, even if it is a belated one. And hopefully, next year will be better. This time for real, do like this video if you enjoyed it, subscribe and hit the bell. Don't forget to leave a comment as well. See you next year.